pattern, and we're going to be looking at special cases of factoring. By the end of the lesson, you will be able to factor expression using patterns of polynomial identities. And are there types of polynomials you can factor using a pattern? If so, what do those polynomial expressions look like? And how can you recognize them? In this lesson, you will think about special patterns that will help you to factor. Question 137 just has us look at special patterns that you should have already learned. Like these are Algebra 1 level problems, okay? And the biggest one or easiest one to recognize is the one called difference of squares, okay? Difference meaning it has to be subtraction. Squares meaning the first term needs to be a perfect square and the second term needs to be a perfect square. So if you know all your perfect squares, 1, 4, 9, 16, 25, 36, and so on, it's going to be easier for you. Decide which of the following expressions below might be a difference of squares. For each difference of squares, show the squares clearly and then write the product. For example, 16x squared minus 9y squared can be rewritten as the difference of squares for x to the second power would be the square of 16x squared, and 3y squared would be the 9y squared, okay? So the first one is a squared minus 4b squared. Hopefully you will recognize that the a is being squared and that the 4b is 2b being squared, and it's a difference, meaning it's subtraction. Then you write it as the product, okay? So the product would be a plus 2b times a minus 2b. The signs are opposite. The opposite signs cancel that middle term. That's why there are only two terms instead of a trinomial, okay? The outside and the inside are opposites because you're multiplying by the exact same thing, and that's why you don't have that middle term, okay? Roman numeral 2 has 2x squared minus 16. It looks like it should be a difference of squares because the 16 is definitely a perfect square. You definitely are having a difference, but 2x is not a perfect square. 2 seems like it should be, but it's not. The square root of 2, sometimes the square root of 2, but you want perfect squares. Okay, so that one is not a difference of squares. Number 3 is negative x squared plus y to the 4th, which when you first look at it, doesn't look like a difference, but if you just switch the order and change it to y to the 4th minus x to the 2nd, then it is a difference of squares because it has a difference. The y to the 4th is a perfect square. It's y squared, and x squared is definitely x squared. So that one is a difference of squares. So when you write it as a product, you're going to do y squared minus x and one of them should be plus. Okay. Doesn't matter which one's plus. You'll notice on this one, I put the plus, then the minus, this one, minus, then the plus. So it doesn't matter which way you write them. And then the last one has a plus sign. We can't reorder it, so it's definitely not a difference of squares. Okay? All right. Any questions on the difference of squares? That should be review, right? You've all seen that before? No. Ugh, okay. Well, now we're going to do it with cubes, okay? So question number 38 says, to factor each of the following expression, use the procedures you developed to identify factors of polynomials. Each final answer should be a linear factor times a quadratic factor. Look for patterns in the factors, okay? So for the first one, we're going to take x cubed minus 1. So we need to fill in a 0 for the x squared and a 0 for the x. And you're going to do your polynomial division using their Polydoku method. You should end up with a binomial times a trinomial. The binomial is already given to you over here, right? It's the x minus 1. You're going to end up with a trinomial up top. That's going to go in there, okay? Same thing for x cubed plus 8. I want you to use x plus 2 as the binomial. You have to fill in the 0x squared and the 0x. But again, you're going to end up with a trinomial up here. That's going to go right there, okay? That's going to lead us to, on the next page, you're going to do those two together. And then on question number 139, it's going to lead us to a very specific pattern. Yes? Yeah, hold on. Is the sums and differences of cubes. Okay, so if you generalize the patterns for the factors in problem 138, you will discover a method for factoring polynomials that are the sum or the difference of cubes. So when it's only a binomial, when it's only a quadratic or second power, it's only the difference. But for cubics, it can be sum and difference. And so there are two generalizations for this one instead of just one. And they are as follows. So you're going to take the cube root of the first term and the cube root of the second term, and that's what you're going to factor out first. Then that's going to leave you with the quadratic. Okay? The quadratics are almost the same. Just notice the differences in the sign. This one has x squared minus ax, and this one has x squared plus bx. So the signs are just the opposite of whatever they are in the original cubic. Move it just into a better spot. Okay, there we go. I think. Okay. So 140 says, in contrast to a difference of squares, a sum of squares cannot be factored using only real number coefficients. For example, consider the quadratic expression x squared plus 9. Okay, for part A, it wants us to discuss what the graph of the quadratic function y equals x squared plus 9 looks like. What are its x-intercepts? Because it's a quadratic, it's going to be a parabola, right? Because it's positive, it's going to open up. It's going to have a y-intercept at 0, 9, which means that one in particular has no x-intercept, and it's floating up above, up here, right? Okay? So if we actually solve that quadratic by setting it equal to 0, subtract 9 from both sides, then take the square root of both sides. But if you take a square root of a negative number, you end up getting that imaginary number, right? The square root of the negative 1 would be the I part, and the square root of 9 would be your plus or minus 3. Okay? So part C says, use the process you learned in section 8.2 to rewrite x squared plus 9 in factored form using the zeros. So one of them would be x plus 3i, and one of them would be x minus 3i. and then they want you to do it as a generalization.